Let me start with a brief introduction. So this year, we are hosting BDD100K challenge in the workshop, and there are two main tracks in the challenge. One is on multi-object tracking, the other is on multi-object tracking and segmentation. And therefore, we will have two winner talks in the coming half hour. The first talk will be given by the PKU team, and by Bin Yan, and the second talk will be given by the Lenovo team. Okay, so without further ado.
Hi, everyone. I'm Bin Yan from Dalian University of Technology. It's my pleasure to introduce our solution, Universal Instance Perception as Object Discovery and Retrieval for this year's BDD100K MOT and MOTS challenge. My presentation today consists of the following parts: instance perception, Uninext, experiments, and video demos. As we know, object-centric understanding is one of the most essential and challenging problems in computer vision. In this work, we mainly discuss 10 subtasks distributed on the vertex of the left cube. So starting from object detection, by replacing the coarse bounding box representation with fine mask, we can obtain instance perception tasks. Then by changing the inputs from static images to dynamic videos, we can obtain MOT, MOTS, and VIS tasks. Finally, when given some extra reference information, such as language expression and target annotations, we can obtain REC, RES, and SOT, VOS, RVOS tasks. According to the properties of the objects, this task can be divided into three classes. The first class aiming at finding objects of specific categories, including image level tasks, object detection, and instance segmentation, and three video level tasks, multi-object tracking, aka MOT, multi-object tracking and segmentation, MOTS, and video instance segmentation, VIS. The second class aims at finding objects referred by specific language expressions. This task includes image level referring expression comprehension, aka REC, and referring expression segmentation, aka RES, and video level referring video object segmentation, RVOS tasks. The final class aims at finding objects referred by target annotations given in the first frame, includes video level tasks in single object tracking, aka SOT, video object segmentation, aka VOS. Since we can find that all the above tasks aim to perceive instance of certain properties, for example, category names, language expressions, and target annotations. So can we design a unified model to solve all mainstream instance perception tasks once and for all? Essentially, all the above tasks aim to find objects specified by some prompts. For example, category names as prompts, including object detection, instance segmentation, MOT, MOTS, and VIS, and language expression as prompts, including REC, RES, and RVOS, and target annotation as prompts, including SOT and VOS. So in this work, we present a universal instance perception model of the next generation termed Uninext, which can unify 10 instance perception tasks into a prompt-guided object discovery and retrieval fashion. In the following parts, I will introduce our Uninext framework. The first key component of Uninext is prompt generation, which transforms diverse original prompts into a unified form. To be specific, for expression-guided tasks, we adopt BERT as the reference language encoder. Specifically, BERT can map the input language expression into a matrix with shape L by D. L is the sequence length, and D is the feature dimension. Similarly, for category name guided tasks, we can concatenate category names into a sentence. Then we send this sentence to BERT to obtain the prompt embedding of the same shape. Finally, for annotation guided tasks, the input is a template image together with the corresponding bounding box or mask annotations. This 4-channel input is processed by a reference visual encoder, such as ResNet50, CountNext, or WAD, to obtain hierarchical feature maps. Then we flatten and merge these feature maps into a prompt embedding with the same shape as the other tasks. Then, given the prompt embeddings and the hierarchical visual features of the current frame, Uninext adopt an image prompt feature fusion module. To be specific, this module is a bidirectional cross-attention, which can first enhance the prompt embedding by the image context and make the original visual feature prompt aware. And the third component, object discovery and retrieval, with discriminative visual feature and the prompt representations, the next crucial step is to transform the input features into instances for various perception tasks. Uninext adopts an encoder-decoder architecture proposed by Deformable Data for its flexible query-to-instance fashion. Based on the prompt-aware visual features, Deformable Data is used to transform n-object queries to n-object proposals. However, not all proposals are what the prompt really refers to. Therefore, we need to retrieval truly matched objects from these proposals. As shown in the right part of the figure, traditional classification is replaced by a unified prompt-guided retrieval. Specifically, given the prompt embedding after a diffusion, for category name guided tasks, we take the feature embedding of each category name as a weight matrix W. The shape of W is 1 by D. Besides, for expression-guided and annotation-guided tasks, the weight matrix W is obtained by aggregating the prompt embedding using global average pooling along the sequence dimension. Finally, the instance prompt matching score S is computed by the matrix multiplication of the target feature and the transposed weight matrix. Different from previous fixed size classifiers, the proposed retrieval had select objects by the prompted instance matching mechanism. This flexible design enables Uninext to joint train on numerous datasets with diverse label vocabularies with different tasks, learning universal instance representations. We trained 3 variants of Uninext with different backbones, including ResNet50, CountNext large, and WAD huge. As shown in these 2 figures, Uninext surpassed the counterparts such as the DN deformable data, query inst, cascade mask RCN, and WAD dat on both object detection and instance segmentation. For REC, RES, and RVOS with language expression as prompts, Uninext also outperformed previous Python methods by a large margin. For tasks which take target annotation as prompts, Uninext also shows superior performance. For SOT, Uninext achieves state-of-the-art performance on 4 large-scale SOT benchmarks. For VOS, Uninext achieved the best results among all non-memory-based methods, largely bridging the performance gap between non-memory-based methods and the memory-based ones. For 3 object tracking tasks, which take category names as prompts, UniNext also obtains state-of-the-art performance, surpassing previously best methods significantly. In this year's BDD MOT challenge, UniNext wins the first place, achieving the highest results on mTheta, mMota, mClass 1, and mMot-P. In addition, this year's BDD MOTS challenge, UniNext wins the second place, achieving the highest mHota, mClass 1, and mMot-P and mIDF1. Here is a video demo of UniNext. The first part is using category name as prompt. Here we put the prompt on the left corner. Different colors represent different object ID. Here we demonstrate both the bounding box level prediction and the mask level prediction results. It can be seen that our method can robustly tracking different objects. The second part is about using language expression as prompts. Different language expression are represented in different colors. And the third part is using target annotation as prompts. Here we shown the 4-channel inputs here. Different tracked objects are using different colors. Our repo UniNext has achieved 1,200 stars. Welcome to follow us. So that's all my presentation today. Thanks for your attention.
Thanks a lot for your presentation. The second winner is unfortunately not presenting live, but we will show the video now.
Hello, everyone. My name is Carl Huang. I come from Lenovo. I'm very pleased to have this opportunity to present our solution for BDD MOT and MOTS challenges. First of all, I want to introduce our contributors for MOT challenge. That is Carl Huang, Bingchuan Sun, Crystal Walter Huanbao, Zhepeng Wang. They all come from Lenovo Research. For MOTS challenge, that is Carl Huang, Feng Chen, Jian Li, Bingchuan Sun, Zhepeng Wang. They all come from Lenovo. Our solution is based on track by detection paradigm. Object bounding box are detected in each image by a detector in MOT. In MOTS, a segmentation head is added to the detector to extract binary mask with each detector box. Our RAID model extract feature from the bounding box. Then, a tracking process the data association to match object ID in the image sequence. For object detection, we use the CBNet V2 architecture, which groups multiply identity backbone and integrate the high and low level features of the multiply backbone network, and greatly expand the recipe file to more efficiently to performance object detection. For this competition, we use the swing transformer backbone with FPNet and HTC detection height. For tracking, we apply the BDD, which tracking by association every detection box instead just the high score one. we combine tracking feature from previous frame with the detection score weight sum. The similarity distance for all boxes is based on RAID distance. The remained high score detection box will be kept as a tentative box until it appears again in the consecutive frame. For the lost and occluding the box, the tracklet will keep for 10 frames in case they will appear again. Based on our high-quality MLT solution, we just add a masked branch to the detection module, and then we try to training it. First, we try to only training mask branch by frozen others part weight, which is got from MLT solution. But this message don't get a very good result on MLTS validation dataset benchmark. We try to find out the reasons of poor performance of frozen network training. We found that there are more things of the NANT and snowy things in MLTS dataset than MLT dataset. Maybe data have some distribution change between MLT and MLTS. So we change the training method. We opened our network weight to do fine-tune based on MLTS dataset. Fine-tune training can achieve better detection performance on snowy and NANT things. For association module of MLTS, we still use MLT box-based RAID for association. Our base version RAID model reference paper, UniTrack, do different tracking tasks require different appearance model. We leverage UniTrack SimClear V2 appearance model, which is per train on ImageNet 1K. Detail association algorithm. We use the hierarchy matching by class. We continue try to improve Orange RAID module. First of all, we found UniTrack RAID model can get better in some NANT things or small object things, maybe because of domain discrepancy between BDD100K and ImageNet. So we try to retrain RAID module. BDD100K dataset have many raw video which is unlabeled, can be allowed as our external training dataset. And we try to leverage our raw BDD100K video to improve our RAID module. For BDD100K dataset, we finally choose the Mocha V2 as our RAID model after performance comparison between the SimClear V2 and the Mocha V2. We crop the object-wise images from the raw images according to bounding box label from MLT dataset. Then we fine-tune Mocha V2 on BDD100K dataset. We don't rely on the tracking annotation to training RAID model and detector model, so our solution just rely on static dataset. Don't need a video sequence annotation. This is our solution final results on MLT, MLTS validation and testing dataset. This year competition, employee mean tracking everything's accuracy, observation M theta as our primary evaluation metric for ranking. This is our final result for competition. Compared with other published team, we get first place in MLTS challenge and second place in MLT challenge. Except tracking by detection paradigm, we also spend many effort to explore an end-to-end paradigm for general MLT challenge. Based on latest paper, MLTR'22 bootstrapped end-to-end multi-object tracking by per-train object detectors. We continue to implement multi-class E2E MLT on BDD dataset, and then change EuroX detector to CVPR'23 detector, and also add BDD100K detection static picture data for training, and change the deformable backbone from R15 to swing B, and then set different threshold by classes. Although many modifications and methods have been attempted in A2E paradigm, unfortunately, the final result is slightly lower than tracking by detection paradigm. Now, summarize our solution. We use the CBNet V2 with the swing B as a detection model, and appearance model training by self-supervised learning, Mocha V2. For track different with the bad track, we change to already association, and also add multi-class NMS and weight reality feature. Another change is that we add a mask hint for detection for MLTS task. Detailed setting, please reference our technical report. This is the major reference. That's all. Thank you for listening.